Space begins just above our heads, but our first real neighborhood beyond Earth may be much closer than distant planets. The Moon. It's airless, stark, and covered in powdery dust, yet it orbits only 3 days away. Hidden in its shadowed craters, scientists have found signs of water ice, the raw stuff for drinking, breathable oxygen, and rocket fuel. Sunlight pours down on its peaks for long stretches, perfect for power. With caves carved by ancient lava and a steady, predictable sky, the Moon could be a training ground where we learn to live off-world. If this kind of journey sparks your curiosity, tap like and subscribe to keep exploring with us. Tonight, we'll map the steps from dusty footprints to our first home in space. Human beings have always moved outward. From early migrations across valleys and coasts to ships that crossed oceans and planes that crossed skies, we have a long habit of pushing past the horizon. We explore to learn, and we settle when a place can support life. That same pattern now points above our heads. Our next near frontier is the Moon. Some of the pressure comes from risk at home. A changing climate can strain water, food, and habitat. A growing population asks for more energy and materials. Now and then, a large asteroid reminds us that Earth orbits in a busy neighborhood. Beyond Earth, however, the solar system holds vast resources. Even a small portion of the asteroid belt contains metals, water-bearing minerals, and other raw material that could feed industry and support settlements in space. The scale is hard to grasp, but the idea is simple. There is far more out there than we could ever lift from Earth. The discovery of water on the Moon has shifted plans from distant hope to near-term engineering. Space agencies and private companies around the world are designing landers, rovers, and cargo systems to return to the lunar surface and stay. Activity on the ground will ramp up in the coming years, scouting safe sites, mapping ice deposits, testing power systems, and learning how to use local materials. Living there brings new constraints. The Moon's gravity is about 1/6 of Earth's, which changes how we move, how machines work, and how fluids behave. There is almost no atmosphere, no air to breathe, and no blanket to block radiation, so sunlight and shadow are harsh. High-energy particles from the sun and from deep space can damage tissue and electronics unless we shield them. Temperatures swing from deep cold to intense heat over a lunar day, which lasts about 2 Earth weeks. When rocks and soil expand and contract under such extremes, they can crack and shift. Apollo seismometers recorded moonquakes, some tied to this daily heating and cooling. All of these factors shape how we build, where we place equipment, and how we schedule work. To stay, we will need to create a complete support loop. Safe habitats must keep pressure steady, filter air, and block radiation. Transport must be efficient, both on the surface and between the surface and orbit. Power must be constant. Solar arrays near bright ridges can help, and small nuclear systems may bridge the long nights. Food, water, and basic supplies must be produced locally as much as possible to cut the cost of lifting everything from Earth. A lunar base would be one of the largest coordinated engineering efforts in history. Teams of scientists and engineers are already laying the groundwork. If they succeed, people may look back at this decade as the start of a permanent human presence off Earth. The Moon itself is a familiar companion. It is the brightest and largest object in the night sky and sits close by on a cosmic scale, about 239,000 miles away. It is also the only place beyond Earth where humans have walked. The first wave of robotic exploration began in 1959 with the Soviet Union's lunar program. Luna 1 missed its landing, but still proved that we could send a craft to the moon's neighborhood. Luna 2 did what had never been done before. It reached the lunar surface, making it the first human-made object on another world. Those early steps were followed by a sequence of unmanned probes that mapped terrain, tested landings, and measured radiation and dust. In 1969, the Apollo 11 lunar module reached the surface, and 2 astronauts climbed down to walk on ground that had never felt a human foot. Their words and images spread across the planet, and the message was clear. We can set goals that seem out of reach and meet them. Over the next few years, 12 more astronauts walked on the moon during later Apollo missions, driving rovers, collecting rocks, and placing instruments. Apollo 17, launched in 1972, marked the end of that era. Afterward, priorities shifted, budgets tightened. For a long time, the moon slipped from the top of national lists. The earlier race to demonstrate capability had been about prestige and power. Once that race ended, plans moved elsewhere, to space stations in low Earth orbit, to robotic missions across the solar system, and to telescopes looking deep into space. A change came in 2009. India's Chandrayaan-1 spacecraft carried a set of instruments, including a spectrometer that looked for the signature of water molecules in sunlight reflected from lunar soil. It found widespread evidence that water, or its close chemical cousin hydroxyl, was present across the surface, especially near the poles where sunlight is weak and cold traps can preserve ice. That result overturned decades of simple models that had treated the moon as bone dry. It became a turning point. Some instruments on that mission saw signals consistent with water ice, not just hydrated minerals, and they mapped places where the conditions might allow it to persist. 2 months later, in November 2009, NASA's L-CROSS mission took a direct approach. A spent rocket stage was sent on a controlled impact into a shadowed crater near the South Pole, and a trailing spacecraft analyzed the plume that rose from the collision. The data showed clear signs of water ice mixed into the ejected soil. In simple terms, there was enough frozen material that, if you could scoop it and melt it, you would get liquid water useful for drinking and cleaning, and as a base for other life support. The Chandrayaan-1 findings had suggested water was present as water, not only bound tightly within minerals, and L-CROSS confirmed that at least some shadowed craters hold it in accessible form. By March 2010, radar data added more detail. A mini-SAR instrument on Chandrayaan-1 reported more than 40 craters near the North Pole with radar reflections that looked like ice, sitting in places that sunlight never reaches. Estimates based on those signals suggested that hundreds of millions of metric tons of water ice might be trapped in permanently shadowed regions. The exact number remains uncertain and depends on depth, purity, and spread, but the scale is large enough to matter. Water is a keystone resource. You can drink it. You can use it to grow plants in controlled greenhouses. You can split it into hydrogen and oxygen through a process called electrolysis, which simply uses electricity to pull the molecule apart. Oxygen supports breathing inside habitats. Hydrogen and oxygen together make high-performance rocket propellant. If we can make fuel on the moon, we can launch from there with much less effort than launching from Earth, because the moon's lower gravity demands less energy. Solar arrays or compact nuclear reactors could power these steps, turning a local supply of ice into a steady stream of essential inputs. On the strength of those discoveries, plans began to firm up. Rovers designed to drill, heat, and analyze soil near the poles will help map ice in place and test extraction methods. The aim is to move from detection to use, to characterize how clean the ice is, how deep it lies, and how it changes with seasons and local terrain. Demonstrations of in situ resource utilization, a phrase that means using what is already there, will help design the first production systems. As confidence grows, missions can scale from kilograms to tons. With each step, the return path looks more practical. Launch supplies from Earth at first, then gradually switch to local water, local oxygen, local radiation shielding made from compacted regolith, the sandy dust and crushed rock that covers the moon. All of this raises a larger question that many have asked. Why build a colony beyond Earth at all? The honest answer is that there are several reasons, and some pull harder at certain times. One is simply that we have always expanded into new environments when we could do so safely. We have settled coasts, deserts, mountains, and islands. Given time and tools, humans adapt. Another is that spreading out reduces risk. A species that lives in more than one place is less likely to be erased by a single event. A third is that new places open new kinds of work and new ways to learn. Population growth adds pressure to find more raw material. While we can and should recycle and use resources wisely on Earth, the supply inside one world is finite. Models of economic and environmental limits have been debated for decades, and they share a theme. Growth on a closed system cannot be exponential forever. Space changes the geometry. The asteroid belt alone contains metals like iron, nickel, and cobalt, along with water locked in clays and ices. Engineers have sketched concepts for free-flying habitats and industrial platforms built from these materials. Some studies argue that, in time, the total living area inside a network of such structures could exceed Earth's land area by orders of magnitude. You will sometimes see figures suggesting 1,000 times Earth's land surface, with room for a population in the trillions. These are long-term visions, not near-term plans, but they illustrate the core point. A solar system economy can be much larger than one bound to a single planet. There are also direct hazards that nudge us to prepare. Climate change is the most present. It alters weather patterns, melts ice, raises seas, and modifies ecosystems. It demands attention and action here at home. Work on space does not replace that duty. In fact, exploration often feeds back into stewardship. Satellites help us watch forests, oceans, and atmospheres. Planetary science teaches us how worlds change under different conditions. Mars shows how a thick atmosphere can thin, and Venus shows how greenhouse warming can run away. Building careful systems for life support in space can inspire more efficient systems on Earth. The two paths inform each other. Under all of these arguments runs a quieter current. People are curious. We like to know what is over the hill and under the ice, what is on the other side of the sea, and what lies in the dark at the rim of a crater. The moon is a natural next step because it is close, reachable in days rather than months, and rich in lessons. The conformation of water there, together with long periods of sunlight on some high ridges, natural caves carved by ancient lava that may provide shelter, and a stable, predictable environment, has turned the moon from a destination for short visits into a candidate for a first home beyond Earth. Living on the moon will still be demanding. Dust is fine and clingy, and it wears down seals and joints. We will need better coatings and filters. The lack of air means every leak matters, so habitats must be built with layers and backups. Radiation means walls must be thick or buried, perhaps using bricks sintered from local soil. Low gravity affects bones and muscles. Crews will need regular exercise and careful health monitoring. Thermal extremes advise designs that use the ground as insulation, like burrowing slightly below the surface or lining habitat walls with regolith. Power systems must survive the long night, which may call for energy storage, nuclear generators, or access to peaks that see near constant sun. Communication with Earth has a short delay, a few seconds round trip, which is manageable, but still shapes how we operate robots and coordinate emergencies. Despite these challenges, the path is clearer now than it was. Start with short missions to the poles. Prove that we can find and use ice. Learn how dust behaves around landers and drills, and how to keep it from coating solar panels and optics. Test lightweight habitats that expand on landing, and then get covered with soil for protection. Use small pilot plants to make oxygen from regolith and water from ice. When each piece is trusted, connect them into a base that can host crews for months at a time. From there, a steady rhythm can grow. Resupply ships bringing specialized tools, cargo landers delivering parts, crews rotating in and out, and, in time, a local economy that produces fuel, spare parts, and research results. Many of the tools we need already exist or are in development. Precision landing systems can touch down within a small zone rather than hundreds of meters away. Autonomous rovers can map, drill, and haul. 3D printers can turn powdered rock into simple structures. Life support systems on the International Space Station have taught us how to recycle water and scrub carbon dioxide from air. Radiation detectors and medical monitoring have improved. When these technologies are adapted for the Moon's environment, they form the backbone of a small but resilient outpost. From the long arc of exploration to a working plan, the logic stays clear. We push outward by habit and by need. We paused after the first space race, then returned when new data showed the Moon holds what could keep us there. The discovery of water changed a gray, silent world into a place where ice can become air to breathe, water to drink, and fuel to fly, turning rock into shelter and a short trip into a possible home. But a plan is only as strong as the world it meets, and the Moon has rules of its own. It is close, yet not friendly. There is no atmosphere. Daylight and darkness last for weeks at a time. Gravity is only 1/6 of Earth's. Temperatures swing by hundreds of degrees. Dust is sharp and clings to everything. Radiation is steady and strong. Tiny rocks hit the ground at high speed because nothing slows them down. Together, these facts set the brief for any base. Thick shielding and careful layouts to cut radiation and impacts. Tight dust control at suits, airlocks, and radiators. Stored power and smart heating for the long night. Steady health measures for low gravity. And, wherever possible, turning local ice into oxygen, water, and propellant to close the loop. The first difference is time itself, or more exactly, the rhythm of light and dark. On Earth, we have a 24-hour day. On the Moon, the diurnal period, the length of the day-night cycle, is very long. Near the poles, some ridges sit in sunlight for most of the year because the sun skims the horizon and barely sets. Other places, they are trapped in shadow for months. At lower latitudes, the pattern is simple and extreme. About 2 weeks of daylight, followed by about 2 weeks of night. A person living there would not see a sunrise and sunset each day. They would have half a month of bright sun and half a month of darkness. Work, rest, plant care, and power use would all have to fit this slow pulse. Inside, crews would almost certainly create an artificial day and night, with lights that dim and brighten on a 24-hour schedule. This helps the body's circadian clock, the system that tells us when to sleep and wake. It also helps keep moods steady and tasks predictable. even when the world outside is bright for days on end or dark for just as long. Energy planning must follow the same rhythm. Solar panels work well when the sun shines, and in some polar spots the sun shines often. But the long lunar night at most sites means power must be stored for many days. Batteries, fuel cells, or small nuclear units can bridge the gap. Heat also needs careful control. During the long day, equipment warms up and must shed heat. During the long night, everything cools down and must stay above freezing. Engineers use radiators to dump heat, insulation to hold it in, and thermal mass materials that absorb heat slowly to smooth out the swings. A base might place its main structures partly below the surface, or line the walls with local soil to make a thick, slow-to-change thermal shell. This thermal buffering reduces stress on machines and helps keep a steady indoor climate. Gravity is the next big change. We call Earth's pull 1g, written as 1 gram. The Moon's gravity is about 1/6 as strong, or roughly 16.6% of Earth's. You would weigh much less and could jump higher, but the real question is what this does to health over years. We do know what months in weightlessness do to people. Muscles shrink, bones lose calcium, fluids shift in the body, and the immune system can weaken. That is under microgravity, the near-zero pull you get in orbit. What we do not know is how the body responds to partial gravity, the in-between level you would feel on the Moon or Mars. Is 1/6 g enough to protect bones and muscles? Is it closer to 0g or closer to full g? We do not have long-term data yet. Most scientists expect a spectrum of effects. The Moon likely helps more than freefall does, and Mars, at about 1/3 g, may help more than the Moon. But these are informed guesses. Until people live in partial gravity for many months, we cannot be sure. Because of this uncertainty, health systems for a lunar base must be active, not passive. Daily exercise will likely be a must, using treadmills, bikes, and resistance devices designed for low gravity use. Doctors may ask crews to wear sensors that track heart rate, bone load, and sleep quality. Diets rich in calcium and vitamin D can support bone health. Some designs add short-arm centrifuges, spinning rooms, or seats to give parts of the body a dose of higher gravity for a few hours a day. Even the layout of a habitat can help. Handholds and foot loops reduce awkward strain. Workstations are set at the right height for a lighter step, and tools have grips that keep hands from over-tightening in a world where everything weighs less but still has the same mass and inertia. Temperature is another strict teacher. Without an atmosphere to spread heat around, surfaces in sunlight can get very hot, and surfaces in shade can get very cold. The swing between lunar day and lunar night is several hundred degrees. Metal, rock, and glass expand and contract with each cycle, and that constant flexing can fatigue materials over time. There is also a link between these thermal extremes and moonquakes. Instruments left by earlier missions recorded different kinds of seismic activity. One set, called shallow moonquakes, sometimes reached magnitude 5, or a little higher. On Earth, a magnitude 5 quake is serious, but often short. On the Moon, ground motion can last much longer, several minutes to 10 minutes, because the dry crust does not damp vibrations in the same way. A permanent base must expect these events, even if they are infrequent. Structures would need flexible joints and shock-absorbing mounts. Tall, stiff towers would be avoided in favor of low, compact shapes. Sensitive equipment would sit on isolation pads. Crews would practice safe modes the same way people in earthquake zones do on Earth. Switch to backup power, secure loose objects, pause delicate work, and check seals after the shaking stops. The lack of air changes almost everything. An atmosphere does many quiet jobs for us on Earth. It carries weather, it smooths out temperature, it shields us from most incoming radiation. It also burns up small rocks before they hit the ground. The moon has none of that. With no air, there is no natural barrier against micrometeorites, dust to pebble-sized bits of rock and metal that fly through space at many kilometers per second. Even a grain of sand at those speeds has the energy of a bullet. Hulls, suits, and visors must be tough enough to take the small hits, and critical areas will likely be buried under a layer of compacted soil to add protection. Radiation is the other main concern. Without an atmosphere and without a strong magnetic field, the surface is exposed to steady streams of high-energy particles. Cosmic rays are particles, mostly protons and heavier atomic nuclei, that arrive from the Sun and from beyond the solar system. The Sun also sends sudden bursts of protons during solar storms. On Earth, our air and magnetic field stop most of these. On the Moon, levels are much higher than on the ground here. They can be lower than in open space because the ground blocks half the sky, but they are still high enough to matter. Over months and years, exposure can raise the risk of cancer, harm cells, and confuse electronics. A base must use shielding from the start. Thick walls made from local regolith, the moon's powdery soil can line habitats. Water tanks can be placed in walls and ceilings to serve both as storage and as a radiation shield. Work rules can limit how long crews spend outside during high activity. Forecast systems can warn of solar events so people can move to storm shelters with extra thick protection until the surge passes. The sun's ultraviolet light also hits the surface without being filtered by air. This UV can break down plastics and sealants over time. Dust, which is sharp and clingy because it is not smoothed by water or wind, can scratch visors and jam joints. Tools and suits must be designed to shed dust and to keep moving parts clean. Airlocks will likely include dust rooms with vacuums, brushes, and sticky mats to keep dirt from getting inside. Materials will need coatings that resist UV and temperature cycling. Pipes and tanks will need flexible joints or loops to absorb expansion and contraction. Cables will be routed so they do not crack when the ground flexes. Even basic chemistry works against easy growth. The moon is poor in volatile elements, substances that turn to gas easily or escape in a vacuum. Nitrogen and hydrogen are two of the most important. Nitrogen helps make a safe breathing mix for people. It also supports plant growth and many industrial steps. Hydrogen is part of water, fuels, and plastics. Some hydrogen is present in ice at the poles and in minerals that hold it weakly, and small traces of nitrogen may exist in certain deposits. But overall, supplies are low. If a base cannot recover enough of these elements locally, it must import them. Once there, it must recycle them tightly. Air will be scrubbed and returned to the loop. Water will be cleaned and reused over and over. Waste streams will be captured for their elements. Closed-loop life support is possible, but it adds complexity and cost. Until steady local sources are proven, the pace of growth will be limited by what can be delivered from Earth or from near-Earth asteroids. These limits do not mean a base is impossible. They define the kind of base that makes sense. It would be compact, careful, and tuned to its site. At a polar location with long periods of light, solar power can be the backbone, and batteries can fill the gaps. At an equatorial site, with equal stretches of day and night, a mix of solar, storage, and small nuclear units can keep the lights on. Habitats will likely be covered with regolith, either piled up by robots or turned into bricks by sintering heating soil until grains fuse. Interiors will keep a human rhythm, with lighting and temperature set to Earth-like cycles. Shops will be built for easy glove use. Rovers will have soft starts and stops to reduce dust clouds. Schedules will avoid heavy outdoor work during the hottest and coldest hours of the lunar day. Planning also respects the unknowns. The health effects of partial gravity require long studies, so early crews may rotate more often and send back detailed medical data. Radiation models will be checked against real measurements in different seasons of the solar cycle. Structures will be instrumented to track vibration and temperature, so engineers can see how they age across many day-night swings. Each of these feedback loops improves the next design. Bit by bit, the base moves from a fragile outpost to a place that can host people for longer stretches. These realities set the baseline for design. Maintain artificial 24-hour light to protect circadian health. Store enough energy to bridge the long lunar night. Use active countermeasures to offset low gravity. Build flexible, insulated structures that tolerate thermal swings. Keep dust out with robust seals and clean airlocks. Add thick regolith for radiation shielding. And recycle air and water tightly where key gases are scarce. With these pieces working together, crews can operate safely for long stretches, while continuous sensing of health, radiation, vibration, and temperature refines procedures and guides the next round of hardware. Once those rules are met, proximity becomes an advantage. The moon's location offers practical benefits no distant world can match. Travel is measured in days, not months. Apollo made the trip in about 3 days with 1,960 seconds technology, and modern vehicles can trim that with better engines and trajectories. Short transit times change risk planning. Emergency cargo and medical supplies can reach a base while problems are still solvable, and a crew that must return can be home within days. That timeline shapes training, spares, and medical support, letting engineers design for repair and replacement instead of demanding every part survive years without help. Distance also shapes communication. Radio and light need about 1.3 seconds to go one way between Earth and Moon. That means roughly 2.5 to 3 seconds for a round-trip exchange. A pause that short is noticeable, yet it still allows smooth voice and video. A doctor on Earth can talk a technician through a fix and see the result almost as it happens. Teleoperation people on Earth driving robots on the Moon is realistic because the control loop is tight enough. Slow, precise tasks like sample collection, valve turning, and careful assembly can be supervised from home with minimal lag. This is very different from Mars, where the delay can stretch from several minutes up to about 20 or more, depending on orbits. On the Moon, you can guide a rover, wait a beat, and see what it does. On Mars, you must plan whole sequences in advance and hope the context hasn't changed by the time commands arrive. That difference opens a middle path in how work gets done. Local crews handle safety-critical jobs and repairs. Teleoperators on Earth handle routine surveys and many repetitive tasks. Autonomous systems fill in the rest. Closeness has a human side too. On the hemisphere that faces Earth, the near side, the blue planet would hang large in the sky, brighter than the full moon looks from here. Its phases would wax and wane on a roughly monthly cycle. That steady presence can ease isolation. A window with Earthlight is not just a view, it is a daily reminder of home. Weather swirling over oceans, night-side cities glowing like a net of fire. Crews on the far side would not see Earth without relays or cameras, because the Moon keeps the same face toward us. But near-side sites offer a direct line of sight for communication and a psychological anchor that matters during long stays. Gravity tilts the equation in another helpful way. Rockets do not fight the same climb on the moon that they do on Earth. With only about 1/6 the surface gravity and no air to push through, the energy needed to lift a payload into orbit is far lower. This shows up in the rocket equation, which links how much fuel you need to how fast you want to go. Lower gravity and lack of atmosphere mean less fuel for the same job, or more payload for the same fuel. If a base can make propellant on site by splitting water ice into hydrogen and oxygen and chilling them into liquid fuels, then the moon becomes a natural depot. Vehicles could launch from its surface with tanks filled locally, meet in lunar orbit, and head onward with much smaller pushes than a launch from Earth would require. The moon would serve as a springboard, a place where fuel is cheap to lift, where stages can be checked and refueled, and where routes to other targets begin with a smaller hill to climb. These practical benefits are part of why many planners view the moon as the most reachable next step for a lasting presence beyond Earth. Mars, main belt asteroids, and near-Earth asteroids are also studied and carry great value. Private companies are testing big rockets and landers. Public programs are maturing systems for deep space trips. NASA's Space Launch System and the Orion spacecraft are being developed for missions that include crewed flights beyond low Earth orbit and eventual orbits around Mars in the 2030s, if schedules and budgets hold. Similar ambitions exist in other countries. Engineers and scientists around the world are using the moon to rehearse the skills that long voyages demand. Navigation beyond the protective bubble of Earth's magnetic field, deep space life support, autonomous surface work, and logistics chains that move cargo between worlds. The moon is not only a waypoint, its nearness lets us practice the whole playbook with backup close at hand. Short travel times and direct lines also invite new kinds of activity. Tourists are not the primary drivers of exploration, yet once transport is reliable and prices fall, short visits become plausible. A trip that fits into a few weeks off work is easier to imagine than a months-long cruise to Mars. Scientific fieldwork can be more frequent as well. Teams can return to the same site across seasons, swap instruments, and grow long records of temperature, radiation, and dust. Industry can try small pilot plants first, an oxygen extractor here, a 3D printing testbed there, and scale up in measured steps without committing to years of isolation. Where a settlement goes on the moon is one of the deepest choices. The site dictates how people live, how they work, and what they can make. Broadly, candidates cluster into three families: the polar regions, the equatorial regions, and the far side. Each family brings its own mix of light, resources, access, and risk. Years of mapping, laser altimeters measuring height, cameras cataloging boulders and slopes, spectrometers reading mineral fingerprints now give planners a detailed atlas. We know which craters stay dark, which ridges see long sunshine, which plains are smooth, and which areas hold basalts, anorthosites, or hints of special elements. With this atlas in hand, the trade-offs become clearer. The poles draw the most attention. Near both poles, some crater floors are so deep and their rims so high that sunlight never reaches them. These are permanently shadowed regions where temperatures drop low enough to trap water ice and other frozen gases over long times. Close by are high ridges and crater rims that receive sunlight for most of the lunar year because the sun circles low on the horizon. These places are sometimes called peaks of near-eternal light. The pairing is powerful. Cold traps that may store ice within easy traveling distance of long-lived solar power. Water is a keystone resource. It supports drinking and hygiene, plant growth in closed greenhouses, oxygen for air, and hydrogen and oxygen for fuel. Long sunlight stretches simplify power management. Panels can deliver steady energy, and batteries only need to bridge short dips. The polar terrain is rugged, with steep slopes, soft regolith, and deep shadows, so careful site surveys and strong mobility systems are vital. But the proximity of energy and water points to a base that can run year-round and grow in stages, adding storage tanks, greenhouses, processing skids, and workshops as confidence builds. A polar base also benefits from cooler thermal cycles. Because the sun stays low, surfaces do not heat and cool as violently as they do near the equator. Temperatures still vary, but the pace is gentler, which helps structures last. Communication links from the poles to Earth are generally good from high ridges, though some valleys and crater floors need relay towers or satellites to keep a clear line of sight. The biggest unknowns at the poles are still the exact form, purity, and depth of ice. Is it patchy frost on grains, thick lenses under the surface, or layers mixed with soil? Different forms call for different tools: warm blades that shave and melt shallow layers, drills that bring up cores, or trenchers that scoop and cart loads to heated bins. Early missions are designed to answer these questions with ground truth, so that later systems can be designed for the actual material, not for guesses. Equatorial regions offer a contrasting set of features. Much of the equator is covered by wide basalt plains, the dark maria that we see from Earth. These plains were once ancient lava flows, so they are relatively smooth and open, which helps with landing and construction. Near the equator, the Moon's orbital plane and Earth's equatorial plane nearly line up, simplifying some launch and transfer paths for material moving between Earth and Moon. There is also a well-known navigation trick called a free return trajectory. This is a path that uses the Moon's gravity to bend a spacecraft's route back toward Earth without a large engine burn. Apollo used such paths as a safety feature, and cargo systems can too. Equatorial sites make those arcs straightforward. Another reason people mention the equator is helium-3, an isotope of helium that has 2 protons and 1 neutron. It is very rare on Earth because it usually comes from the decay of tritium, which is scarce outside nuclear facilities. The lunar surface, exposed for billions of years to the solar wind, may have trapped small amounts of helium-3 inches, the top layers of soil. Some hope that a future fusion reactor could use helium-3 inches reactions that produce less radioactive waste. The practical reality today is more modest. Even if helium-3 exists in higher concentrations at the equator, it is likely to be spread thinly through large volumes of soil, so mining and separating it would be complex and energy-intensive. Current science suggests that making helium-3 on Earth from tritium is cheaper than hauling it from the Moon. Fusion itself is also still in research. For now, helium-3 is best viewed as a long-term possibility, not a driver for first bases. Power is the equator's downside. The day-night cycle near zero latitude gives almost 2 weeks of daylight and almost 2 weeks of darkness. Those long nights demand huge energy storage, careful heat control, and work schedules that can tolerate long pauses or a switch to nuclear power. Without light, batteries drain, machinery cools and contracts, and lubricants can stiffen. Systems must be built for hibernation or designed to run through the cold using stored energy. It is possible, but the design grows heavier and more complex than at the poles. On the other hand, equatorial sites on the near side enjoy constant line of sight to Earth, which simplifies communication and reduces the need for relay satellites. Traffic patterns add one more equatorial benefit. Launch windows from Earth to equatorial near-side sites are frequent, and the geometry supports those free return arcs that bend a craft back home if needed. For bulk shipments of durable goods, metal parts, electronics, construction materials, this can be attractive. Flat plains allow simple roads and rail-like tracks for moving cargo, and the mare basalts may offer uniform regolith that is easier to process into bricks and paving blocks using sintering or microwave methods. The far side is different again. It is radio quiet because the moon itself blocks Earth's constant hum of transmissions. That makes it uniquely valuable for radio astronomy, especially at low frequencies that our ionosphere blocks and our civilization floods with noise. A large radio telescope or a network of radio dishes spread across a far-side plane could listen to faint signals from the early universe, map the structure of our galaxy, and watch the sun's radio bursts without interference. The lack of atmosphere helps optical astronomy as well. There is no air distortion, no twinkling, and no weather to cloud a mirror. Stable bedrock offers firm foundations for precise instruments. The trade-off is communication. There is no direct line to Earth from the far side. Relays would be needed in lunar orbit or at a gravitational balance point beyond the moon to pass data and voice. For a scientific outpost or an automated observatory, that is a reasonable cost. For a settlement that depends on steady contact with Earth, the added complexity must be planned from the start. Choosing among these families of sites depends on goals. If the priority is to learn how to use local resources, especially water, then a polar location near both light and ice holds the lead. If the goal is to test high-throughput cargo lanes and simple construction on open ground, then near-side equatorial plains offer smooth terrain and easy communication at the price of long nights. If the aim is to build quiet ears for the universe, the far side is unmatched. In practice, development may not be a single point, but a network, a polar base that grows into a small town of power stations, storage tanks, labs, and habitats, an equatorial pad that serves as a cargo hub and test range, and a far-side science park linked by relay satellites, all sharing standards for docking, power, data, and maintenance. Across all options, the moon's closeness keeps logistics grounded. A cargo lander can sail on a free return path for safety, then break into orbit and drop to a prepared pad. If something fails, the supplier can try again within weeks, not years. Training can be staged in steps. One mission to scout and sample, the next to leave behind power and communications, the next to test a pilot plant, and the next to add a habitat. Teleoperators can add labor from Earth without flying more people. The short communication delay means software updates, procedures, and fixes can be tested live with the people who need them. Even psychology benefits from the cadence. Crews can keep regular contact with families, see sunlight on familiar continents, and share day-to-day life with Earth in ways that long-delay missions cannot match. Fuel production is where proximity may pay the largest dividend. If polar ice is confirmed in forms that are practical to harvest, a chain can be built from extraction to storage to launch. Warm tools loosen icy regolith. Heaters turn it to vapor. Condensers collect liquid water. Filters clean it. Electrolyzers split water into hydrogen and oxygen. And cryocoolers liquefy the gases into propellants. Tanks then feed ascent vehicles, tugs, and landers. Every kilogram of fuel made on the moon is a kilogram not lifted from Earth's deep gravity well. Over time, this shifts where it makes sense to assemble missions. A spacecraft bound for Mars could be launched dry from Earth, with empty tanks and robust hardware, then fill up at a lunar depot. That architecture spreads work. Earth builds complex parts in heavy industry. The moon supplies bulk propellants and raw shielding material. Deep space tugs move pieces into the routes that lead outward. None of these advantages erase the hazards. They set a frame where the hazards can be managed with tools we can build and test. Short travel time is not only good for emergencies, it is good for iteration. If a drill clogs, a new bit can fly. If a solar array shows dust buildup beyond predictions, the next shipment can include better brushes and electrostatic wipers. If health sensors show that partial gravity leaves bones vulnerable, the next habitat can ship with a compact centrifuge for daily sessions. The feedback cycle is fast enough that lessons reach the hardware while crews still remember the context. That is a quiet strength of the moon that no distant target can match right now. As site studies sharpen the maps and missions add data, the picture turns practical. Polar ridges are charted for month-by-month sunlight and shadow. Free return paths are tuned for different cargo masses and launch sites. Far-side relays prove handoffs and data rates. Equatorial test pads practice dust-safe landings with throttled engines and lessons from recent probes. Step by step, closeness becomes a system routes, depots, pads, and procedures that make movement routine rather than heroic. With that network in place, the focus shifts from getting there to staying there. Once a site is chosen, the question becomes where and how to build so people and machines stay safe. The surface looks simple, but it is not gentle. There is no atmosphere, so high-energy particles from the sun, solar particle events, short bursts of protons can sweep the ground, and a steady background of cosmic rays arrives from deep space. Tiny rocks strike at speeds far beyond a bullet because nothing slows them. On top of that, temperatures can swing by hundreds of degrees between bright ground and deep shadow. Any base in the open must handle all three at once: radiation, impacts, and heat. Shielding is the first layer of defense. On Earth, air and our magnetic field do most of the work. On the moon, walls and soil must do it. A simple rule helps planners. More mass between you and space equals less dose. Thick shells made from local material can block many solar particles and reduce cosmic rays. Burying pressurized rooms under a cover of lunar soil cuts the hit rate from micrometeorites too, because the loose grains spread and stop incoming fragments. Thermal control then keeps the inside steady while the outside bakes and chills. Insulation slows heat flow. Radiators and heat pipes carry extra heat away during the long day. Heaters and stored energy keep systems warm during the long night. Given these pressures, many scientists suggest building where nature already provides cover. Ancient lava once flowed across the moon, cooled at the surface into a crust, and continued running beneath that lid like a hot river. When eruptions faded, some of those rivers drained and left behind hollow tunnels. These are lava tubes. We see similar features in places like Hawaii and Iceland on Earth. On the moon, they can be very large because lower gravity lets the rock span wider gaps without collapsing. Openings called skylights, deep holes with sharp rims mark where a roof has fallen in and reveal empty space below. A settlement tucked into a tube would be protected from solar storms, most cosmic rays, and flying grit. It would also be shielded from the hardest temperature swings. Models suggest a fairly steady interior temperature, around a few tens of degrees below freezing, roughly the 20 degrees Celsius, which is cold but predictable. Living underground brings trade-offs. People need sunlight for mood and health, so habitats would include bright, full-spectrum lights and window-like panels that show real-time views from cameras on the surface. Air must be circulated through long passages. Pressure must be held by strong liners and bulkheads. Emergency exits must be planned with redundancy. A tube lets engineers place modules side by side, add storage tanks along the walls, and run cables and pipes with fewer outside penetrations. Rovers can dock at a covered entrance where airlocks trap dust. Over time, teams can carve niches for labs, farms, and workshops, using rock bolts and liners the way miners do, but with a cleaner, more controlled approach. Crews would still spend time outside for science, maintenance, and exploration. Radiation doses are manageable for planned walks, and the tools and habits learned inside the tube would make those trips safer. Underground is not the only path. Another approach is to build on the surface and pull the ground up over the top, turning the base into a series of low, covered mounds. The blanket material is regolith, the moon's layer of loose, broken rock and dust made by countless meteorite hits. People often call it soil, but true soil on Earth includes organic matter from life. Lunar regolith has no organic content. It is mineral fragments only. The grains are sharp because there is no water or wind to smooth them. They include glassy bits formed by impacts and tiny specks of metallic iron mixed into oxides and silica, silica being the base of common glass. Regolith is useful precisely because it is everywhere and easy to move. Bulldozers, bucket wheels, or conveyor belts can scoop it, haul it, and pile it over habitats and power systems. A layer, a meter, or two thick can cut radiation to safer levels and stop most small impacts. To build roads, landing pads, and walls that do not kick up dangerous dust, the loose grains can be sintered, which means heated until they fuse together into a solid crust. Microwaves do this well because those tiny iron particles and other minerals absorb microwave energy and heat from the inside out. In labs on Earth, simulants of lunar soil have been melted into solid tiles using microwave sources not much stronger than a household oven. On the Moon, larger microwave units, solar concentrators, or electric kilns could make bricks, pavers, and curved panels. Robots could lay them in interlocking patterns that resist cracking during the long, hot, cold cycle. Microwave sintering is only one tool. Concentrated sunlight can focus heat to fuse the top few centimeters of dust into a hard, glass-like surface. That turns a risky, dusty landing zone into a clean pad and gives rovers firm tracks that do not sink. Large 3D printers can extrude pastes made from ground regolith mixed with binders produced on-site, then cure them into arches and shells. Inflatable pressure modules, light fabric rooms can be placed on level pads and buried under regolith for protection. Over time, the outside becomes a quiet hill of native material. The inside stays at shirt sleeve conditions with a steady temperature and bright, controlled light. Radiation rules shape every layout choice. Water is an excellent shield, so tanks can be placed around sleeping areas and control rooms to add protection while doing double duty as storage. Food stores also add mass to walls. A small storm shelter with extra thick shielding sits near the center of the base. When space weather monitors warn of a solar flare, crews move there for a few hours while the worst of the proton storm passes. Instruments on the surface measure dose rates, and work shifts adapt to avoid long outdoor tasks during active periods. Electronics are housed in shielded racks and tested for tolerance. Critical systems have backups and lightning-fast switchover. Micrometeorites and larger meteoroids are a separate threat. Most objects that reach the moon are tiny, but they arrive at tens of kilometers per second. A pressurized wall has multiple layers: an inner pressure bladder, structural ribs, a spacing layer that spreads out the force of a hit, and an outer bumper. Piling regolith on top helps even more. For exposed equipment like solar arrays and radio gear, protective berms and angled shields deflect debris. Landing and ascent pads are placed far enough away that rocket exhaust does not blast grit at living areas. Where crossings are needed, covered trenches carry cables and pipes below grade so a stray rock cannot cut power or air. Heat is the quiet background problem that never goes away. The long lunar day bakes surfaces. The long night chills them. Materials expand and shrink with each cycle. Designs limit the number of penetrations through pressure walls and use flexible bellows and loops in pipes to absorb motion. Cables have slack and strain relief. Bearings and seals are kept warm with small heaters. Dust is kept outside with air showers and electrostatic brushes in airlocks. The ground itself can serve as a thermal buffer. Burying rooms a few meters down reduces the daily swing. In polar regions, where the sun skims the horizon, swings are slower and smaller, which makes life easier. Living underground at first does not mean people will never build in the open. It is more like a phased plan. Early bases use tubes or buried modules for safety and learning. As power grows and shielding methods mature, more structures can rise above the cover. Greenhouses with thick, clear panels. Workshops under domes, made from sintered blocks. Towers for communications, and weather stations that can survive quakes and thermal strain. The cultural image is not a cave forever. It is a campus that starts inside rock, because that is the smart place to begin, then adds surface spaces when the tools and data support it. Regolith handling will become an everyday skill. Rovers will mine it like snowplows, collecting it into hoppers. Conveyor belts will move it to foundations. Compactors will press it into dense layers. Sintering rigs will print pads in hexagonal tiles. Over time, roads link landing pads to habitats and storage yards. The very dust that first seemed like an enemy becomes the backbone of the built environment. Each load stacked on a roof is one less load that had to be launched from Earth. Because the moon's hazards are different from Earth's, safety rules are tuned to the place. Helmets and suits have micrometeorite-rated visors. Work outside happens in pairs with a rover nearby for quick shelter. Airlocks are sized for tools and sample bins, so dust stays outside. Every module has a clear path to the storm shelter. Quake sensors listen for shallow moonquakes. When motion starts, equipment that could tip or crack goes into a safe state. Pressure doors can be closed in seconds to isolate a leak, and emergency kits hang at regular intervals with patch materials and oxygen masks. Training drills make these steps routine, so the response is calm when alarms sound. The most promising ideas are tested with robots before people depend on them. A small crawler can place a string of temperature probes in a lava tube and map air currents. A hopper can fire a small microwave sintering unit at a patch of regolith, then measure how strong the crust becomes after weeks of thermal cycling. A pilot plant can bake scooped soil to drive off trapped water and measure how much is truly there, not just hinted at by orbiters. These ground truths turn sketches into engineering numbers. They also reveal surprises which always arrive when plans meet real dust and real rock. As methods mature, construction becomes a rhythm. A lander touches down on a pre-hardened pad and releases a pack of autonomous graders, haulers, and bricks made on the previous mission. They assemble berms, thicken shields, and lay new pads. Pressurized modules arrive, inflate, and are quickly covered. Power systems grow panel by panel along ridges that see long sunlight, while compact reactors provide baseload through local night. Inside, light follows a 24-hour cycle, and the air is kept clean and calm. Outside, the base looks like a set of low hills and dark roads, with antenna masts and sensor poles breaking the horizon and a few skylight domes glowing softly where people spend time with real views of the sky. Once a site is chosen, the next task is how to build a first base that protects people and machines from radiation, micrometeorites, and extreme temperatures. Designs have evolved as maps, materials, and mission data have improved. Early ideas reused lander frames or emptied fuel tanks for living space. Later concepts added inflatable rooms that launch small and expand after landing. A parallel approach favors pre-integrated structures. Assemble and test the habitat in space, then land it as a single unit with life support, controls, storage, and work areas already connected. This reduces surface assembly in dust and cold, but demands a precise touchdown on a prepared pad and strong legs to absorb loads. If the unit arrives level and powered, basic operations can begin within hours. With these build methods in hand, the next question is placement, whether to set habitats inside natural voids or on the surface under protective cover. The choice between lava tubes and surfaced, regolith-covered structures is not either or. Different sites and missions will use both. Tubes offer instant shielding and stable temperatures. Surface builds offer easier access, simpler expansion, and direct lines to the sky. Over time, a mixed layout makes sense. Long-term sleeping quarters and storage inside rock, greenhouses and workshops under armored domes, labs and telescopes on the surface, where instruments need open views. What ties the layout together is a simple rule. Use what the moon provides: rock for mass, stable voids for cover, long sunlight on the right ridges for power to lower risk and raise safety. Then add human systems to tune the environment for steady work and rest. Step by step, the ground becomes a partner in construction rather than something to fight. Dust is the persistent obstacle. Lunar dust grains are micrometers across, angular and abrasive because there is no wind or water to smooth them. Repeated micrometeorite impacts grind rock into this powder, a process geologists call impact gardening. In sunlight, solar wind charging makes dust cling to surfaces and creep into gaps. Apollo crews reported scratched visors, jammed joints, irritated eyes and lungs, and suit fabrics that heated unevenly after dark dust coated them. Dust also settles on solar panels and radiators and can contaminate seals. Because there is no rain, designs must prevent entry rather than rely on cleanup. One way to limit exposure is to assemble and verify the habitat in Earth orbit. Test all seals, filters, and loops under microgravity. Then fly the finished unit to the surface, so only external hookups and shielding remain. Even then, dust control is a daily routine. Airlocks can use suit ports so the suit stays outside and the person climbs in from the rear, keeping dirty layers out of cabins. Brushes, vacuums, and electrostatic wands remove grains before re-entry. Electrodynamic dust shields thin electrodes that produce traveling electric fields, can push charged particles off windows and radiators. Radiators mounted vertically collect less dust than horizontal panels. Pads and roads can be fused into crusts, so wheels and lander plumes do not loft clouds. Cables and joints are covered by flexible boots. Each step reduces wear, heat control problems, and air quality issues. 3D printing provides a second construction path. In contour crafting, robots extrude paste in layers to form walls and shells. The feedstock can be local regolith mixed with a binder such as sulfur or a geopolymer made on site. Sulfur melts and rehardens at modest temperatures. In vacuum, it sets into a strong composite with regolith grains. Layer by layer, printers build ribs, arches, and domes that match site constraints. Because the moon is near, operators on Earth can supervise printing with the short radio delay, steer the nozzle, watch the bead, adjust flow, verify adhesion, move on. Early work can proceed without a crew on site. A binder-free option is sintering, which heats regolith until grains fuse. Microwaves couple efficiently to lunar soil because it contains metallic iron and iron oxides. Grains heat from within and lock into a dense, glass-like solid. Concentrated sunlight or electric kilns can also make tiles and bricks. Tests with lunar simulants have produced pavers and beams with strengths comparable to lower-grade concrete. Printers can embed ducts for wires and pipes while building, protecting lines from dust and thermal cycling. The output is not decorative. It is a hard shell that takes small impacts, blocks radiation, and moderates temperature. Hybrid systems combine an inflatable pressure core with a printed shell. A lightweight, airtight module lands, inflates, and passes a pressure test. Robots then print vaults and add thick regolith layers over the hull. The printed lattice spreads loads. Loose regolith above it supplies extra shielding. The inflatable provides clean, rapid startup for air, water, and power. Because most mass comes from local soil, only a small fraction on the order of 10% of structural mass must be launched from Earth. This ratio lowers cost and risk and lets crews focus on interior setup, connecting life support, arranging storage, planting initial crops under grow lights, and calibrating instruments. Before any large lander arrives, a small mission can prepare the ground. Microwave or laser units fuse a broad circle of regolith into a landing pad that resists erosion by rocket exhaust. Berms of compacted soil surround pads and living areas to catch debris. Covered trenches carry power and fluid lines below grade, so a micrometeorite cannot sever them. Standard docking points let new modules latch onto the grid quickly. Site plans, reserve routes for future tanks, additional airlocks, a greenhouse corridor, and a laboratory branch. So growth does not force risky relocations later. Natural shelter can further reduce risk. Lunar lava tubes form when a flowing sheet of lava crusts over, while molten rock keeps moving below. As the flow drains, a tunnel remains. Lower gravity on the moon allows wider, more stable spans than on Earth. Skylights collapsed, roof holes reveal access points. Models and thermal data suggest tube interiors sit near a steady cold temperature around 20 degrees Celsius, which simplifies thermal control. If a tube near the site is stable, robots can survey it with LiDAR and radar, place anchors, and line sections with pressure-tight membranes. If no suitable tube exists, surface construction with buried pre-integrated modules and printed shells provides similar shielding and thermal stability. Habitability and life support set many details. Water is an excellent radiation shield and thermal mass, so tanks back sleeping areas and control rooms. Air loops hold oxygen, carbon dioxide, and humidity within tight limits. Filters capture fine dust before it can reach lungs or electronics. Airlocks include suit cleaning tools and cargo vestibules. Interior work surfaces and storage are sized for gloved hands and low-gravity handling to avoid joint strain and accidental float-offs. Sensors track air quality, temperature, and radiation in real time, with clear alerts and simple checklists. A compact storm shelter sits near the center. with extra shielding for solar particle events. Crews move there for a few hours, when space weather monitors warn of a proton surge. Quake sensors detect shallow moonquakes. Equipment enters safe modes to reduce stress during long vibrations. Assembly sequences aim to minimize outdoor exposure. First deliveries provide power, communications, and a small rover team with grading and inspection tools. They level the site, harden pads, and place beacons for precision landing. The pre-integrated habitat, or inflatable core, lands next, connects to power, and undergoes leak checks. While humans activate systems inside, robots print shells or pile regolith over the hull. Additional units bring storage, greenhouses, and workshops. After each step, teams verify radiation dose at key locations, dust in airlocks, temperatures in critical bays, and vibration loads. Results guide adjustments to shielding thickness, heater settings, and work schedules. Because of the short light time, many operations can be teleoperated from Earth. Supervisors drive printers and haulers in long shifts, hand off to another team across time zones, and keep work moving while the crew sleeps. New software and procedures are tested in simulation and then applied within days. If a test exposes a weak joint or an abrasive dust behavior, redesigned parts can ship on the next cargo flight. This fast loop turns site experience into hardware changes while memories are fresh, cutting repeat errors. Interfaces matter as the base grows. Standard power connectors with dust caps, quick disconnect fluid fittings, and common data links let new vehicles and modules join without custom work. Inside, racks follow common sizes so equipment swaps without rewiring. Outside, printed curbs improve rover traction on ramps and reduce edge crumbling. Wayfinding lights and cameras aid docking in low sun angles. These small, repeatable standards reduce accidents and shrink the time from delivery to useful output. Energy is the shared dependency for every path. Mining, hauling, printing, sintering, life support, communications, and science all draw steady power. At polar sites with long periods of light, solar arrays can serve as the backbone, with batteries and fuel cells bridging short gaps. Panels need dust-resistant coatings, wipers, or electrostatic cleaners to maintain output. At sites that face 2 weeknights, compact fission reactors can supply constant baseload while solar handles peaks. Waste heat from reactors can warm nearby structures and reduce electric heater demand. Power lines run in shielded trenches and feed switchgear that isolates faults and balances loads. Storage sits near the systems it serves. Batteries for printer surges, thermal storage for greenhouse temperature control, hydrogen and oxygen tanks near ascent pads for fueling. Multiple construction methods are likely to be used together. Where a tube is safe and accessible, lining and sealing it can yield rapid shielding and stable temperature. Elsewhere, a mix of pre-integrated modules buried under regolith and printed shells can reach the same safety levels. Pads and berms reduce plume erosion and debris. Covered trenches protect utilities. Suit ports, dust shields, and clean airlocks keep cabins free of contaminants. Water-backed walls, storm shelters, and work rules manage radiation. Sensors and drills verify conditions, and teleoperation extends labor beyond the crew. With each addition, another power string, another covered module, a longer, hard-surfaced road, the site shifts from a one-off camp to an expandable system. The common element across concepts is using what the moon provides: regolith for mass and shielding, natural voids for cover, long sunlight at the right ridges for power, and adding proven pressure vessels, filters, and controls to create rooms that hold steady air and temperature. As data accumulates and tools are refined, Assembly becomes a repeatable sequence rather than a one-time stunt, and the first base gains the functions needed for longer stays and larger teams. A lunar base needs a steady source of electric power. Without electricity, nothing else works. Air is not moved, water is not cleaned, heat is not controlled, and tools do not run. Several options can supply that power. Solar energy is the simplest to start with because it is free at the point of use, scales from small to large, and has few moving parts. Panels can be fixed to frames or laid on the ground and tied into batteries and inverters. Many of the raw materials for solar cells and frames exist on the Moon in some form. Silicon is common in lunar rock. Aluminum, magnesium, and calcium can be refined from regolith for structures. Glass for covers can be made from melted regolith. Making complete, high-efficiency panels on the Moon will take time and complex chemistry, so early missions will bring finished panels from Earth. Then, add more local content as smelting and glassmaking improve. The hard part for solar is the long night. Near the equator, one lunar day lasts about 354 Earth hours, almost 15 days, followed by a night of similar length. Panels make no power during that night. A single site must carry enough stored energy to run life support, communications, heaters, and basic tools for 2 weeks, or it must have another source. One engineering answer is to build a network of solar fields spread across long lines of sight. As the sun sets at one site, it rises on another, and power can be moved between them by cables on the surface or by beaming microwaves between towers. This is complex, but it avoids shutting down for half the month. Another answer is to place power stations where sunlight is nearly constant. Some high ridges near the poles see the sun for most of the year because the sun stays low in the sky. Panels there can generate for long stretches and send power by cable to nearby bases. Solar has a straightforward upside. There are no clouds on the Moon, no weather, and no air to absorb sunlight. When the sun is up, output is stable and easier to predict than on Earth. Dust must be kept off arrays, but electrodynamic cleaners, wipers, and smart placement can help. A third method shifts panels off the ground entirely. Arrays in orbit around the Moon or in special balanced locations can collect sunlight all the time and beam power down as microwaves to a rectenna, which is a receiving antenna that converts microwaves back to electricity. This space-based solar power avoids night and shadows on the surface, but it requires heavy lift for the first arrays, precise pointing, and careful safety rules for microwave beams. It is more likely to follow after surface systems prove themselves. Nuclear fission is the other main option. A small reactor produces steady power day and night through dust storms, which do not exist on the Moon, and long shadows. One compact fission unit in the tens to hundreds of kilowatts could meet the needs of an early base, and multiple units could run a larger site. Reactors do not care about the 354-hour night, so they remove the need for huge batteries. They do require launch safety, strong shielding, and large radiators to dump waste heat into space. Hardware must be tested for startup in vacuum and low gravity. On the positive side, reactors can be buried under regolith for extra shielding, and the same shielding protects people from radiation coming from space. Transporting a reactor is costly and demands approvals, but once in place, it simplifies operations. Most bases will mix sources over time. Solar arrays can carry daytime loads and charge storage. A small reactor, or later a larger one, can supply baseload, run heaters through local night, and serve as a backup for medical or life support emergencies. The right mix depends on site and mission. Polar sites with long light can lean on solar. Equatorial sites with long nights benefit more from fission or very large storage. In all cases, power must be stored because loads do not match the sun perfectly, and short gaps and surges happen even at the poles. Energy storage is its own challenge. Batteries work well but are heavy. Mass matters because every kilogram sent from Earth costs money, and every kilogram moved on, the Moon takes effort. Lithium-ion batteries are the current standard, with good efficiency and long cycle life. Other chemistries such as sodium-sulfur can store more energy per kilogram and operate at higher temperatures but require careful thermal control. Hydrogen fuel cells are another mature system. A fuel cell makes electricity by combining hydrogen and oxygen. The byproduct is water and heat. In spaceflight, fuel cells have run for more than 2 weeks, which is long enough to bridge a lunar night. The water they make can be stored and then split back into hydrogen and oxygen by electrolysis when the sun returns. This regenerative fuel cell cycle lets a base store energy as chemical fuel during the day and turn it back into electricity at night. The trade-off is mass. Tanks, plumbing, and catalysts add weight and volume. Designers balance battery packs against fuel cell systems based on the power profile of the base and the expected growth path. Thermal storage can help in specific cases. During the day, electric heaters or focused sunlight can store heat in a material such as molten salt or a block of dense rock. At night, that heat can keep greenhouses or workshops within range without using as much electric power. Flywheels and compressed gas can cover short surges. For the first missions, the most practical plan is simple. Solar panels carry the day. Batteries and fuel cells carry the night. And careful power management stretches reserves by scheduling heavy tasks when sunlight is available. Power alone is not enough. A base becomes livable only when it has a reliable life support system. Life support is the set of machines and rules that keep air, water, food, and temperature within safe limits. It also handles waste so resources can be reused. On the Moon, life support must be closed loop as much as possible because importing supplies is expensive. Using local resources called in situ resource utilization reduces the load on supply ships. The most important in situ resources for life support are water, oxygen, and hydrogen. Water can be mined as ice near the poles or extracted from minerals that hold it weakly. Electrolysis splits water into hydrogen and oxygen. Oxygen is used for breathing and for fuel, and hydrogen is used for fuel and as a reagent in some extraction steps. Oxygen can also be pulled from regolith by heating and reduction, because lunar soil contains many oxides. In time, both paths will likely be used together. Water ice feeds drinking, and plant needs first, while oxygen production from regolith builds larger stockpiles for air and propellant. Air inside the habitat is kept at a stable pressure with the right mix of oxygen and nitrogen. The Moon is poor in nitrogen, so early supplies will come from Earth and be conserved carefully. Carbon dioxide exhaled by people is scrubbed from the air by filters or by chemical beds that can be heated to release the captured CO2 for reuse in plants. Humidity is controlled by condensation and drying cycles, so mold does not grow and electronics do not corrode. Temperature is kept in a narrow range by heaters, chillers, and heat exchangers. Water is cleaned in loops that include filters, reverse osmosis, distillation, and biological steps for breaking down waste. These methods are already used on the International Space Station and can be adapted for the Moon with added protection against dust and wider thermal swings. Food production closes the loop further. Plants can turn carbon dioxide into oxygen and produce fresh food that adds vitamins and variety to stored meals. Studies with lunar soil simulants and samples have shown that plants can grow when given water, light, and nutrients. The main missing ingredient is organic matter. Regolith has no humus or living microbiome. It is crushed rock with bits of glass and oxides. To grow crops in regolith, it must be amended with compost, fertilizers, or a manufactured nutrient mix. An easier path for early farms is hydroponics or aeroponics. In hydroponics, plants grow in water with dissolved nutrients. In aeroponics, roots hang in air and are misted with the solution. Both methods use less water than soil and allow tight control over nutrients and pH. They also reduce dust risks because growth chambers are sealed and clean. Agriculture on the moon faces specific stressors. The surface outside swings between hot and cold extremes, and there is no air to move heat around. Greenhouses must be sealed pressure vessels with strong windows or covers. Radiation from space can damage DNA in plant tissues over time, so growing areas need shielding, usually by being partially buried or covered with thick, clear materials that block high-energy particles. Solar flares can add short, intense bursts of radiation. Operations plans include safe modes for greenhouses during these events, such as moving trays into shielded racks or closing shutters. Pollination is another issue. Many crops do not require insects. They self-pollinate or can be pollinated by shaking, airflow, or hand tools. For crops that do rely on insects on Earth, robots and simple air currents can stand in. Live pollinators may be tested later, but early systems will likely avoid that complexity. Light is the key input for plants, and the long lunar day and night create a scheduling problem. Lighting a farm with LEDs through a 354-hour night uses a lot of power. There are several ways to manage this. One is to place farms near the poles where sunlight availability is higher and power is steadier. Another is to design crop cycles around the sun. Pick fast-growing varieties, start them under LEDs when a new day begins, and harvest before night falls. Short crops like lettuce, radishes, and herbs fit this model. A third way is to use a mixed lighting plan. Fiber optic concentrators or mirrors can pipe daylight into sealed rooms while the sun is up. Efficient LEDs then carry the load at night with spectra tuned to photosynthesis. Waste heat from lights helps warm growing rooms. Extra heat can be moved into thermal stores for the night. Carbon dioxide from the crew can be metered into the farm to boost growth, and oxygen from the farm flows back to the habitat. Farming also ties into water cycles. Condensation from plant leaves can be captured and returned to tanks. Nutrient solutions are filtered and reused. Solid waste from kitchens and plant trimmings can be composted in sealed bioreactors to make a safe fertilizer. Sensors watch every part of the loop: oxygen levels, CO2 levels, humidity, solution chemistry, light intensity, and temperature. If one measure drifts, software adjusts pumps, fans, or lights. Over time, data help pick the best crop mixes for taste, nutrition, and reliability. Fresh food then becomes routine instead of a special delivery. Power, storage, and life support reinforce one another. A reactor's steady output makes it easier to run lights at night. Solar's daytime peaks line up with heavy tasks like electrolysis and metal smelting. Regenerative fuel cells close the loop between power and water. Waste heat from power systems warms greenhouses and workshops. Radiators placed in shade keep electronics cool. When a base plans these links early, it needs less margin everywhere else. That lowers the mass that must be launched, shortens setup time, and raises safety. Before people depend on any of these systems, they are tested with robots and short crew visits. A pilot plant near a polar site can mine, melt, and electrolyze ice into oxygen and hydrogen, measure energy use, and report how filters clog and seals age. A small greenhouse can run for a full lunar day and night cycle with LEDs, then for a second cycle with daylight assist to compare power and yields. Battery packs and fuel cells can be cycled through deep discharges to see how they perform in vacuum and cold. Each test adds numbers that replace guesswork. With numbers, engineers can size arrays, tanks, and radiators correctly and set work schedules that fit the real curve of the Sunday. As systems mature, the power network grows like a spine across the site. Arrays spread along ridges or on tracked mounts that keep panels aimed at the Sunday. Cables run in covered trenches to protect them from micrometeorites and dust. Switchgear isolates faults quickly so a cut line does not darken the whole base. Storage sits near major users to reduce losses. A fueling yard with hydrogen and oxygen tanks stands close to an ascent pad. A farm zone clusters near warm waste streams. A control room watches flows on simple, clear screens and can hand control between local crew and teams on Earth as shifts change. With this kind of layout, the base can add modules, fields, and racks in a known order. Power and life support stay in balance while construction continues, and a small station becomes a place that runs day after day with steady routines rather than crisis management. A permanent lunar base also needs transportation that works from Earth to the Moon and across the surface once you arrive. The distance is about 239,000 miles. So the first problem is simply getting there in a reliable, repeatable way. Today, the proven path is a conventional rocket that lifts a spacecraft to Earth orbit, performs a burn toward the Moon, and then uses another burn to slow into lunar orbit and descend to the surface. Modern launchers and landers are being designed to reuse major parts so costs fall over time. Navigation can follow free return routes that swing past the Moon and back to Earth without large engine burns, providing a built-in safety option during the early phase of development. There are also gentler ballistic capture trajectories that trade time for lower fuel use, helpful for heavy cargo. All of these options keep the basic idea intact: staged propulsion, precise timing, and careful braking near the surface. A more radical concept is a lunar space elevator. The Moon's weaker gravity and lack of atmosphere lower the bar for a tether, because the cable does not need to fight thick air or extreme winds. The idea is to anchor a strong fiber near the lunar equator and extend it toward a balance point in space so that small climbers can ride the tether rather than using rocket fuel. Materials such as high-performance polymers have been studied for this, and models show that a lunar elevator is far easier than an Earth elevator. Even so, it remains a long-term proposal. A tether must resist micrometeorites, thermal cycling, and wear from repeated climbs. It needs active control to stay stable. Until those engineering risks are retired, rockets remain the practical tool for moving people and cargo between worlds. Moving across the surface is a second, separate system. Terrain varies from smooth basalt plains to fields of boulders and steep crater walls. Dust is everywhere and can be abrasive. Designs range from small, open rovers similar to the Apollo vehicles to large, pressurized rovers that let crews work for days without wearing suits. Open rovers are light and simple. They carry tools and samples over short ranges, in good weather, meaning when radiation is low and temperatures are manageable. Pressurized rovers are mobile labs with air, heat, and workbenches inside. They allow longer trips to drill cores, deploy instruments, and survey ice. Power for both can come from batteries, fuel cells, or a mix. Fast swap battery packs and standardized charging posts reduce downtime. For operations near the poles, where the sun stays low, rovers can park with panels angled to the light. For night operations or heavy work, fuel cells provide steady energy and produce water that goes back into the life support loop. Hopping or flying vehicles are another tool for hard terrain. In one idea, a hopper uses a small amount of propellant to make short arcs over ridges or into crater floors where wheels cannot go. Low gravity helps, and there is no air to fight. The trade-off is dust. Rocket plumes can sandblast hardware and kick grit into joints. Hoppers need dedicated pads at both ends and careful thrust control. Small sky cranes that lower payloads on tethers are also possible for placing instruments on rough ground without landing the main vehicle. Over time, a mixed fleet emerges: crewed rovers for local work, autonomous cargo trucks for hauling regolith and parts, hoppers for special jobs, and walking robots for tight caves and lava tubes. Teleoperation adds reach without adding crew. The signal delay from Earth to the Moon is under 3 seconds round trip, which is short enough for people on Earth to drive robots with careful, deliberate motions. Operators can lean in with cameras, feel resistance through haptic controls, and place instruments with millimeter precision. This is useful for early construction grading pads, laying cables, and printing walls before a large crew arrives. It also continues later as a way to multiply local labor. When a rover gets stuck, a second team on Earth can help free it, while the on-site crew focuses on safety-critical tasks. For a base to move from an outpost to a community, self-sufficiency must grow. Transport only pays off when most mass stays local and only high-value parts flow in. That is where mining and processing come in. The Moon's surface layer, called regolith, is rich in oxides of oxygen, silicon, aluminum, iron, and other elements. Several processes can turn this mix into useful materials. Hydrogen reduction of ilmenite, an iron titanium oxide found in basalt, can release oxygen at moderate temperatures if hydrogen is supplied and then recycled. Molten regolith electrolysis can split the oxides directly, yielding oxygen, gas, and pools of metal alloys that can be cast into parts. Water ice, if present in reachable deposits near the poles, can be heated to vapor, condensed, cleaned, and split into hydrogen and oxygen. These paths support life support, first air and water, then expand into construction materials: glass for windows, ceramics for insulators, aluminum and iron for beams and panels. Once materials flow, a local industry can take shape. Simple components like bricks, pavers, and radiation shields come first, because they only require heating and shaping. Next are pipes, tanks, and structural frames made by casting or additive manufacturing. Wiring and electronics remain imports for a long time, but even partial local manufacture now saves mass on every flight. The aim is straightforward: reserve Earth launches for high-complexity items and send bulk mass only when the Moon cannot yet supply it. Propellant production is the most direct way lunar industry reduces the cost of spaceflight. Liquid oxygen and liquid hydrogen made from polar water can be stored in insulated tanks and used to refuel landers and tugs. Oxygen is the heavy part of most high-performance propellants, so making oxygen locally matters, even if hydrogen is still imported at first. Storage is a challenge, because cryogenic liquids boil away unless cooled. Engineers can reduce losses with multi-layer insulation, sun shields, and zero boil-off cryocoolers powered by solar arrays or reactors. Depot's simple stations with tanks, pumps, and docking ports can sit in low lunar orbit near the planned gateway orbit or at balance points between Earth and Moon. Vehicles top up there before heading outward, or they refill before returning to the surface. A similar depot in Earth orbit can service satellites and reduce the need to throw away hardware when fuel runs low. With depots in place, the transportation architecture changes. A cargo lander can launch from Earth mostly empty, meet a tanker at a depot, fill up, and then descend to the Moon with a large payload. After delivering, it can refuel on the surface and return to orbit to meet another tanker. The same lander can fly many cycles, which spreads its construction cost across many trips. Crew vehicles can use the same nodes, but carry extra safety systems and redundant engines. The key is to standardize docking, fueling, and data so that different vehicles can use the same infrastructure. Over time, routes become regular. Earth to depot, depot to lunar orbit to surface, and back, with schedules built around sunlight at the sites and the energy needed for each hop. As activity grows, the Moon becomes a logistics partner for the wider solar system. Mines near the poles ship water and oxygen to orbit. Metal parts flow upward to workshops that build trusses, tanks, and shields in microgravity conditions where large, delicate structures are easier to assemble. Fiber drawing and alloy casting in low gravity can produce goods with properties that are hard to achieve on Earth. Once these products exist in orbit, they can be moved using efficient electric propulsion that sips propellant and pushes gently for weeks or months. The result is a stepwise shift. Heavy, low-value mass, like propellant and radiation shielding, comes from the Moon. High-value, complex systems still come from Earth until a later phase. The idea of a deep space gateway, now commonly called the Lunar Gateway, fits into this network as a node rather than a destination. Placed in a near rectilinear halo orbit around the Moon, it can host crew for short stays, stage landers, and act as a relay for far-side operations. If it supports propellant transfer and life support resupply, it becomes a rest stop where vehicles check out before long burns to Mars or asteroids. A fuel-rich cislunar region lowers the energy barrier to the rest of the solar system. Every kilogram that does not have to climb from Earth's deep gravity well saves multiple kilograms of fuel, which compounds across a mission. In practical terms, refueling near the Moon makes bigger payloads and more flexible mission designs possible. Commercial opportunity follows these capabilities. A lunar mining firm can sell water, oxygen, and shielding mass to any customer in cislunar space. Government programs, private stations, or satellite servicing companies. A construction company can print landing pads, roads, and berms on contract and lease pressurized garages for rovers. Manufacturers can make simple structural parts on the Moon and ship them to orbit. Insurance and maintenance services appear once there are enough assets to support. The business case is still sensitive to launch prices and the pace of technology, but the direction is clear. Local supply lowers cost and risk for everyone who operates beyond Earth. Self-sufficiency does not mean isolation. The base still needs a steady flow of high-precision tools, computers, medicines, and replacement electronics from Earth. But the heavy, repetitive mass propellants, water, oxygen, bulk shielding, bricks, can come from the ground underfoot. Each ton sourced locally frees a launch for something that cannot yet be built away from Earth. Each refueled flight increases the return on the depot system. As these loops tighten, the threshold for new missions drops. A science team can schedule more frequent fieldwork, A telescope firm can plan a far-side array without shipping all of its structure from Earth. A Mars mission can leave from cislunar space with full tanks and fresh maintenance, rather than pushing everything out of low Earth orbit in one surge. Water sits at the center of this plan because it supports both people and propulsion. It is split to make oxygen for breathing and hydrogen and oxygen for fuel. It is stored in walls as radiation shielding. It is recycled through farms and cabins and turned back into fuel in regenerative loops. Storing it at depots between Earth and Moon turns the route into a ladder with many safe rungs rather than one long jump. That makes exploration safer, more regular, and less expensive. It also makes the Moon a practical partner, a nearby place that supplies mass and staging to the rest of human activity in space, while developing its own surface transport and industry. Surface mobility, cislunar transport, mining, depots, and life support connect in a single system. Rovers carry drills to the ice. Plants that melt and electrolyze feed tanks. Tankers lift to orbit and fill depots. Landers refuel and repeat. Workshops turn metals and glass into parts for the next round of construction. Teleoperators guide robots through shifts from control rooms on Earth, while crews maintain the equipment that must be handled by hand. As reliability grows, more routes open, near side to far side with relay support, pole to equator along hardened roads, surface to orbit on regular cargo flights. Each piece makes the others more useful, and each mile driven or flown adds to the knowledge needed to keep the system running for longer stretches. Building a permanent base on the Moon gathers many separate demands into one project: a safe site, dependable power, working transport, and an economy that makes the outpost useful. Taken together, these make it one of the hardest engineering efforts humans have ever attempted. The difficulty is not a reason to stop. It is a guide to how careful the steps must be. Even before people return, several missions have laid groundwork by mapping and measuring the Moon in detail. A key example is NASA's Lunar Reconnaissance Orbiter, launched in 2009 and still circling the Moon. Its instruments have made high-resolution images of landing zones, tracked subtle changes in surface temperature, and mapped elevation so landers can avoid slopes and boulder fields. It has also surveyed radiation levels in different regions and highlighted where hydrogen, often a tracer for water ice, appears near polar craters. These datasets reduce guesswork. They point to safe paths, promising resource deposits, and routes for rovers that avoid hazards. Multiple space agencies have described paths back to the surface with longer stays in mind. Plans vary in pace and budget, but they share a pattern. Start with robots, test power and communications, try resource use on a small scale, and only then send crews for longer work. Some proposals come from national programs. Others frame the Moon as a place where many partners can contribute different pieces. One widely discussed idea is a shared outpost, often called a Moon village. The concept is not a single building. It is an open invitation for industry, universities, and governments to add modules and services that work together. Robotic teams could begin by printing pads and covering small habitats with local rock and dust, known as regolith, to block radiation. Power plants would go up on ridges that see long sunlight, and relay towers would keep constant links to Earth. When early systems prove stable, short crew visits would start, growing into longer rotations as life support closes its loops and dust control improves. The aim is to make a place that supports science, technology, testing, and resource work, rather than a one-time flag and footprints event. This shared outpost also serves as a test stand for deeper trips. Living a few months at the poles teaches crews how to manage long logistics chains, partial gravity, and radiation exposure, while still having short travel time to Earth. Transport vehicles can practice docking, refueling, and engine restarts in cislunar space, the region between Earth and Moon. Rovers can prove they can mine ice and move tons of material, not just grams. Greenhouses can run through full lunar day-night cycles to measure power needs and yields. Each lesson rolls directly into designs for longer voyages, including Mars expeditions that must work far from Earth's quick help. Other agencies have built steady programs with their own goals. One set of missions studies landing, sampling, and long-distance roving. Another looks at the far side and polar operations. Some proposals explore the possibility of mining scarce isotopes such as helium-3, an isotope of helium rare on Earth and embedded in the Moon's surface layer by the solar wind. Advocates see it as a candidate fuel for future fusion reactors. The near-term science is more basic. Measure how much is present, how deep it sits, and how hard it is to extract. The same is true for metals and oxygen tied up in regolith. Robotic drills, ovens, and small processing plants can answer these questions before anyone builds a full-scale mine. There are also concepts for a fully robotic base that prepares ground and power before any crew arrives. In this model, a cluster of landers brings in small reactors or large solar arrays, communications equipment, and a team of autonomous graders and haulers. They level terrain, fuse landing pads, and build berms that trap dust and debris. A radio relay keeps constant contact with Earth, and routine maintenance is done by teleoperation, taking advantage of the short signal delay. When the site meets targets for power, radiation shielding, and stable temperatures, pressurized modules arrive for the first human rotation. Some of the earliest sustained activity may come from tourism and short-stay visits. Commercial firms already sell suborbital and orbital flights. The next step is a trip that loops around the Moon or stops in lunar orbit before returning home. The route uses proven physics, a free return path that swings a spacecraft around the far side and back to Earth without a large engine burn if needed. As vehicles grow, firms may add near-surface passes or controlled visits to a staging platform in lunar orbit. Later, a small number of crewed landings could be offered once pads, shelters, and rescue plans are in place. The appeal is clear. Seeing Earth rise over the horizon, watching long shadows move across craters, and visiting the far side that never faces us. For tourism to be routine, systems must be reusable, rescue options must be real, and medical support must be built into every stage. Private companies are not only eyeing tourism, they are building heavy-lift rockets, landers, and surface robots meant to sell services, delivery to the surface, power by the kilowatt hour, refueling in orbit, and data links for science packages. Public programs can buy these services instead of inventing each part alone. This public-private model spreads cost and risk across many missions and rewards. Reliability. A company that can land a one-ton package accurately and often will find customers in science, resource work, and infrastructure. A company that can lay down hardened roads and pads will be hired by anyone who wants safer landings and cleaner operations. The outcome is a network rather than a single project. The idea of staging from the Moon to other worlds fits naturally into this network. If water ice near the poles can be turned into oxygen and hydrogen, a local propellant plant can fill tanks for landers and tugs. A depot in lunar orbit or at a gravitational balance point can store these propellants and sell them to passing spacecraft. Missions bound for Mars or asteroids could launch from Earth with empty or partly filled tanks, meet a tanker near the Moon, fill up, and then depart. This reduces the mass that must be lifted from Earth's deep gravity well and turns the moon into a practical springboard. The same depots can refuel satellites near Earth that would otherwise be retired, extending their life and cutting debris. When many customers need the same things, power, shielding, mass, propellant, landing pads industry grows to meet those demands. A mining company digs and sells oxygen and water. A construction firm prints berms, walls, and roads from regolith. A transport firm operates reusable landers between the surface and orbit. An operations company maintains communications and navigation beacons. Insurance, training, and medical services follow as the number of assets grows. Each company starts small, proves a product, and then scales by adding more units. The moon's closeness makes that path achievable, because repairs, upgrades, and new parts can arrive in days rather than months. None of this removes the need for careful oversight. Launching nuclear hardware, managing microwave power beams from space, and building pressure vessels where people live all require strict safety rules. Environmental monitoring must track how rocket plumes, excavation, and waste streams affect the local area so future science is not compromised. Cultural and scientific heritage sites, historic landers and footprints need standoff distances and clear flight rules. Communications must be coordinated so far-side radio astronomy can operate without interference. Planning these norms early makes later growth smoother. At the same time, the work brings a wider set of benefits back to Earth. Better recycling and closed-loop life support improve how we manage water and air at home. Tougher coatings and seals designed for dust and ultraviolet radiation extend equipment life on Earth. High-efficiency power electronics and batteries built for long lunar nights can help stabilize renewable grids. Remote surgery, teleoperation, and augmented reality support tools developed for crews far from hospitals can aid care in remote regions. Even the simple habit of designing systems to be repaired rather than thrown away has value in many industries. Costs matter across all of this. Reusable rockets and mass-produced landers bring prices down by flying often and by using common parts. Standard docking ports, power plugs, and data links prevent waste and let different vehicles share infrastructure. Modularity allows upgrades without rebuilding the whole base. Software across fleets simplifies training and allows one control room on Earth to supervise many robots. These practical choices turn large goals into repeatable tasks. Timelines, of course, depend on budgets, tests, and steady progress. Some milestones can move faster than others. A rover that hardens landing pads and prints simple walls could operate within a few launch cycles once a site is chosen. A small propellant pilot plant could try melting and electrolyzing ice and log how much power it really uses. A pressurized rover could complete multi-day traverses around a polar base, while a greenhouse runs through an entire lunar day and night. With each verified step, the next one becomes easier to justify. Several national programs set the stage for these steps in different ways. One coalition frames a polar base as a shared laboratory, cargo port, and test range. Another focuses on sample return and far-side work, building toward longer surface campaigns. Proposals for robotic outposts describe graded pads, modular shelters, and automated logistics that can run through the long night on reactors or on batteries charged from polar light. Goals include testing extraction of oxygen from regolith, measuring ice purity and depth, and proving that a lander can fly multiple sorties without major overhaul. Each piece of the picture improves confidence in the next. Interest from wealthy technology leaders has added momentum by funding new vehicles, engines, and factories. Large reusable boosters are being built in parallel with uncrewed landers sized for cargo and crew. This approach, build, test, fly, revise, echoes earlier eras when private capital and public needs drove rapid gains in ships, railways, and aviation. The difference now is the environment: airless, cold, and far from quick rescue. That is why public agencies still set standards, certify safety, and keep backup systems in place. The mix of private speed and public oversight can create a durable path if each side respects its role. Tourism will likely ride along these developments rather than lead them. Early trips may be flybys or visits to stations in lunar orbit. Surface stays require pads, shelters, rescue options, medical support, and clear rules. When these exist for science and industry, visitors can be added carefully. The sights will be unique: the far side's quiet radio sky, the long shadow of a crater wall at local dawn, and the slow change of Earth's phase from a small, thin crescent to a bright, full disk. Travel agencies will plan with conservative margins, and operators will use the same reusable hardware that supports work flights. As more hardware arrives, interoperability becomes the unseen glue. A rover from one company must charge from another's power post. A habitat must accept a visiting lander's umbilical and data feed. A depot must pump oxygen and hydrogen at common pressures and temperatures. Navigation beacons must broadcast on agreed frequencies. When parts work together by design, new players can join without redesigning everything. Standards, bodies, and working groups can draft these interfaces early so vendors can build to them. The early years on the Moon will be a mix of cautious steps and direct tests. Light, well-instrumented missions will scout and verify. Systems that pass will be enlarged. Systems that fail will be redesigned. Success will not look like a single ribbon cutting. It will look like a steady rise in useful mass on the surface, a growing number of vehicles that fly more than once, and a set of services that new missions can buy instead of build. In that pattern, the Moon becomes more than a destination. It becomes a place that supports other work: science, manufacturing, propulsion staging, because power is steady, transport is regular, and local material can be turned into what the next task needs. The idea that Earth could stop being our only home does not rest on a single breakthrough. It rests on many small, proven links: accurate maps, strong pads, clean air, steady power, safe vehicles, and parts that fit together. Agencies and companies are already testing those links. As each one becomes reliable, the next can be added with less risk. The result is not a leap into the unknown, but a careful buildup of capacity. From that capacity, longer stays and farther trips become practical, and the path outward stays anchored to what has been measured and made to work.